Yes, I am a postdoc at University of Toronto. I work on bioinformatics on new generation sequencing data. Something I read apart from my personal guru, God, Jeffrey Hinton's these bunches of paper, is a paper which Yoshua Bengio just recently published. And I was super excited looking at the paper because it seemed like they had cortical circuits which were doing backpropagation, and I always heard Jeff Hinton saying that our brains basically have learned over evolutionary timescales some version of backpropagation. So I was thrilled because I thought this paper has electrophysiology data to prove that backpropagation works. Only after quickly browsing the paper I realized, well, they just cooked up these neurons to behave with voltage gated perceptrons, and they kind of show that it can be mapped back to a neural net which does backpropagation. So it was a bit of a downer, but it's an interesting paper. That and the other fact that heart is the first organ that develops in vertebrate. That was something I read, which was crazy. With that, I would like to start today's talk, which is this classic paper, visualizing data using t-SNE. This was the paper that we intended to discuss, and what I learned is that there are a couple of papers that basically needs to be discussed in the same context, because there was initially a paper called SNE from where everything started. So if we go next, the outline of the talk is basically organized in this way that I will kind of first give you a little teaser that why you should be excited about t-SNE, and then I will slowly develop the theoretical framework of t-SNE, which is the math behind it. And so the way I will do it is I will introduce SNE and then basically say how SNE can be mutated to make a variant which is t-SNE, which was the paper which came 6 years later in 2008. And after that, there was an 8-year gap when people from Google Research wrote this amazing blog article about how to use t-SNE effectively. That's something I think I cannot touch because we don't have interactive access here, but that's something I would love that you guys go back home and try it out. That kind of will touch a lot of points which are the weaknesses of t-SNE. After that, I will basically focus on the discussions, which will be the second half of the talk, which is sort of the points which we will kind of come back maybe to this slide during the discussion, and then we'll go onward from there. So there are two papers which are interesting here. One of the papers is this, again, a paper from the first author of the classic paper. Is a single author paper where he essentially changed the whole game. So the original t-SNE paper which we are discussing was horribly slow. It could only do academically interesting projects. What this paper did was, in 2014 is when t-SNE really caught the market, because they made it from n square to n log n. And after that, in 2017 and 2018, there is another paper where there is so this paper essentially made t-SNE to be possible for 10,000 points. Now this paper can make it to 1,000,000 points. So that's basically where we are right now, and we'll go further. Yeah. So next. So this is just like a teaser. If you do a Google search on t-SNE, you see around 10,800 results pop up. I tried to be a little bit more quantified by going on Web of Science, but unfortunately Web of Science probably doesn't like machine learning so much. It's more for medicine people. But this is a plot from Web of Science where these numbers are not interesting because they have just too little data. But what it does say is that t-SNE papers are all from these different sectors. So all the way from computer science, which is obvious, to genetics, physics, medical informatics, everywhere t-SNE is being used. So it's an amazing, in that sense, a technology which was developed as something which can help to go down into actually doing machine learning if you have a big data, to just clean up, pre-process, and get your features, and then go down after visualizing. So we'll go down, we'll have a next slide. This is a slide I put in because I am personally very much vested into genomics, but without being very biased, t-SNE is actually most heavily used right now in genomics. That's the field that it's being used a lot. And what it does is essentially we have this technology from Illumina, which is a sequencing company called 10x, which sequences a bunch of tissues, and then you basically have inside that tissue, let's say, different cell types, and these cell types are essentially individual columns in a matrix. So every column essentially is represented in a 20,000 dimensional space, so that means they have 20,000 features. So it's a classic data to prove the power of t-SNE, because you have very high feature dimensional here, and what you want to learn is how we can kind of segregate in an unsupervised way all these different cell types. And the colors, of course, come from some kind of different clustering method. So you can do a k-means clustering or something. But what's important is this granularity, that you can go from such a high dimensional space to this. This is what kind of really changed the whole game of single cell genomics, where we are right now. One more. So this is a classic homework problem to show that what's kind of the effectiveness of t-SNE, that you can like fire up a Jupyter notebook and see. So this is the MNIST data, which all of us know, and how the MNIST data looks in, if you just visualize it in a PCA plot, is that big blob of every digit, like overlapping with every other digit. But this is essentially the t-SNE visualization of exactly the same data set. So this is kind of already shows that it's quite powerful. It takes all that. How many data points are there in MNIST? Like 70,000? Huh?
10.
60,000.
70,000, right? So this is the full 70,000 data set which I used here. And you can see that it's quite effective. So if you do this exercise at home, though, I will tell you, it will not work out like this. You will not get this result immediately, because what people do a mistake is they essentially take the data and then directly apply t-SNE on it. You can't do that. There are certain other tricks which you have to do, which I will cover in the topic later. So that's the practicals of t-SNE. We'll go over it. Next slide. And this is something which I have not yet been able to wrap my head around, that how to get there, but I think Xiang can be an interesting person who is interested in this. So this is actually from Karpathy's blog. So we all know that he's an amazing guy. What he essentially showed is, he took all these images and he made this proposition that if you train a big, let's say CNN kind of a beast on these images, and then take one of the layers where all these information features of the images are stored, and visualize that on a t-SNE, then this is basically the output which comes from that. So what happens there is, I don't know if you can see it quickly, but all the kind of dogs are somewhat here, and all the kind of birds are somewhat here. So it's amazing that if you can, this slide I put in just to kind of motivate you guys that t-SNE is not just an algorithm to make pretty plots, it can make you money. Because this is how Google image essentially recalls images back. So that's how you could, if you start thinking in that way, that how can t-SNE make product, this is how it can make you product. So it would be interesting to learn more about it, and there are some interesting kind of teasers in the t-SNE paper at the very end, which I think none of these big guys ever followed up on. So if you guys are interested, it would be an interesting thing to follow up on. So okay, so now next slide. Okay, so now let's get dirty with the actual stuff. So to begin with, let's understand what are we trying to do here. So what we are trying to do is we are trying to take some data which is high dimensional, which means that this data is of either two kinds. So either somebody has given you data points like x1, x2, x3, x4, a large number of points, and each of these points has a lot of coordinates. So it has like a1, a2, a3, a4, and like n coordinates. So, and this n is typically, let's say, larger than 100. So that means it's a large 100-dimensional vector. So you can either get a data set like that, like lots of large vectors as data points, or somebody gives you essentially there are lots of high-dimensional data points, but what I give you is not those vectors, but the distances of those objects. So the pairwise distances, okay? So the input is either pairwise distances between, let's say, these high-dimensional points, or the actual coordinates of the high-dimensional points. Everybody is on the same page? Good. So what we are trying to do is take these kind of objects and take step one, which is choose a distance metric. So you have to know whether I'm gonna take a Euclidean distance. If you have text data, maybe you will take a cosine distance. This is all like experimental, but you kind of stick with one. And then you have, again, a choice of different methods by which you will basically transform this data into a lower dimensional space. That's the goal. That's the step two. So this is where you have a couple of options. So you have a PCA or MDS. These are kind of linear transformations. Apparently there's a version or a variant of MDS when it becomes non-linear, but the way it's MDS, classical MDS is it's linear. And non-linear methods. So this was where kind of a bunch of methods have been developed, and Jeff Hinton kind of argues that t-SNE is the very best in this paper. And the field has not moved much, except the fact that there has been a new development called UMAP, which I am sure at some point we will go. But essentially, we will focus on this particular thing called SNE t-SNE. And I will try to motivate what is exactly that changed the game. What is different? All these methods are nonlinear methods. They are essentially transforming the data with some kind of nonlinear function. But t-SNE is doing something very different, which is essentially it's reducing it to a low dimensional manifold so that you can visualize it in 2 to 3 dimensions. That's what the program does. So you cannot visualize, you cannot just take this data, like PCA you can do in 50 or you can do in 100, you can do in whatever, right? But this t-SNE can only give you either 2 or 3 dimension reduction. Typically it is done in 2 dimensions to visualize it. And what you can do is only visualize it. There is no feature selection that you can do with this method. What I kind of discussed is that SNE uses either vectors pairwise similarities or vectors. And what is very different is that it takes function that knowing a point, what's the probability that all other points around me are in some distribution. And using that object, it starts to kind of, like cook a tool. So we'll go there. I want to discuss for a quick thing. We'll go back to discussions later on this thing in context to all these other methods, which is local versus global. So this is something we have to appreciate, that imagine you have a data. That data may have a local structure. So if you how many of you have seen Swiss roll? You have seen Swiss rolls. So a Swiss roll is essentially almost like a ribbon, like it just goes around. So in the Swiss roll structure, what happens is you can roll it out, but distances, local distances actually is what matters. Because what happens is, as you are moving, let's say colors are changing as you move inside to the core of the Swiss roll. It's what the local distances matter. So if you can stretch out the Swiss roll or you can make it smaller, the distances between individual points make no sense. So that's kind of a local object. So think about it in a different way, because maybe the Swiss roll is not an obvious example. Imagine there are lots of points which are connected in a network. So your nearest neighbors to you are your local structure. And the more further you are going out from the nearest neighbor, that gives you a global structure to the object. So what t-SNE cares is to embed this local structure more better. So it wants to keep points which are locally close, very much close in the low dimensional field. But in doing so, it trades off with the fact that points which are moderately close to the point may be actually very far apart in the final map. So this is the trade-off that t-SNE does. I will keep going to this point. It's a bit difficult point to get across, but yes.
Just to clarify on the Swiss roll thing.
Yes.
So what you're saying is the local structure is, so the global structure is the spiral itself.
Yes.
But the local structure would be, if you zoom in on one of those places in those spirals, like this smear of points is close to each other.
Not really. So what happens typically when people plot Swiss rolls is they put a color on top of it. So what happens is, like, imagine at the Swiss roll is like this kind of object, right? So at the very end, so imagine you are going from red to blue.
Okay.
So at the very core are blue colors.
Got
So
it.
if you just do a PCA, you can just unfold it, and it's just a straight line. All the colors are separated. That's what you want to visualize, right? So it works in that case. The actual distances between the red and the blue is very big, but it doesn't matter. What matters is that all the reds are close to each other, all the blues are close to each other, greens are. So that's a local object, local information.
I see. Got
Okay. Let's go. Okay, so there's an amazing video on YouTube called StatQuest. I highly recommend you guys to check any algorithm that you want to learn about. If it's shallow learning, they have a video on it. I tried to kind of replicate it, and I kind of failed horribly because I'm not good at animations, but that's okay. So I have my physicist's way of explaining this. So in a very simple way, what we are trying to do is going from high dimension to low dimension. And unfortunately, as human beings, we can only visualize 2, 3, or 1 dimension. So let's take a 3-dimension, 2-dimensional, like plot here and unfold it into 1D. That's like our simplest t-SNE. So what t-SNE essentially does is, so imagine this is kind of borrowed from the StatQuest idea. So imagine this is the collection of points that you see in 2D. If you start just projecting it on the x-axis or the y-axis, all these points will not necessarily separate out nicely. They might just sit on each top of each other and you will not be able to visualize it nicely. So what essentially the heart of t-SNE does is, it takes a new axis, let's say from xy it goes to some axis called u, and in u it just randomly projects all the data points with some random engine. It just makes coordinates on that point. So everything is dropped there, so there is no order now. Then it essentially decides that things which are similar have some sort of attraction, things which are not similar have some kind of like charges, they repel. And just by so it's very interesting intuition that this is what you would have done in physics. We have this Thomson problem. You throw away charges on sphere and you want to calculate where charges go. They did the same thing here. They essentially threw these points on this line, and they said that these particles essentially either attract or repel, and by minimizing these two pairwise interactions, they essentially end up moving points through each other and get this nice structure where everything is separated out. That's the most core visualization that I can build, but please go and check out StatQuest. You will be amazed what this guy, how he explains it. So okay, next.
A quick question.
Yes.
So the pairwise interactions, if you're thinking of in that way,
yes,
is attractive to some distance, and then it becomes repulsive after that?
Absolutely.
So you have kind of like a
cutoff.
Yeah, like a, what is it called, Van der Waals kind of thing?
Yes, absolutely. Wait, next slide. So again, here there's this little picture which I took from their StatQuest thing. What happens is he draws this essentially thing that, imagine that's now the distribution in the high dimensional space. You choose an object, so the black is our object of interrogation, and from that object we draw all these pairwise distances, okay, all these distances. So now what you do is you plot them on a normal curve, and here I just want you to develop this intuition. What is going to happen is that these 3 blue points are closer to black points, right? So, but in this normal curve, what happens is that this is basically the probability, right? So this essentially closer points have higher Pij values. So this is essentially an object which I'm calculating P, so I is my black point and J is all the other points. So closer points have a higher Pij and further points have a lower Pij. So they are on the tail of the normal curve, and that's something which I need you guys to understand, so that when we go to the math we will use that. Yes?
How do you decide which side of the normal curve it goes on if distance is positive?
That's a good question. How do you decide which side it goes on? Can anybody help me with that?
So, to be very frank, that is one of the drawbacks of this t-SNE, is that when you look at t-SNEs and when you look at the clusters, the placement of those clusters actually don't matter. So this is something random. For example, in one particular iteration of yours, you might find red color on this side and yellow on the other side, but then the next iteration probably you will find blue on the other side, and so it's very random. So that's the thing, the cluster, the placement of the cluster really doesn't really matter. It's just that you have clusters and what are the data points in that cluster. That's important.
Gotcha. So the plus minus is randomly assigned.
Yeah.
Got it.
I should have thought about it. Okay.
What why normal? Like, what is normal?
Actually, it's a
about
Gaussian distribution that they use, but why normal? That's a good question. So t-SNE actually doesn't use a normal distribution.
Okay.
I will get to that. Yeah. Let's just build for the sake of discussion. All I need you guys to understand is that this probability distribution, which is calculated, has a lower value for higher distance points in high dimension space and a higher value for closer points in high dimensional space. Another thing for the sake of the talk is, whenever I say data, it means in high dimensional space. Whenever I say map, it means the low dimensional space that I'm going to. Okay, next slide. Okay, so what this guy does is, another thing which you have to, which is again important, is that this distribution that we will generate somehow needs to be scaled with the fact that with all these distances that you calculate. So for example, there are several distances which you have calculated. There is a problem that if for example this guy there, which we were integrating, if that is a bit sparse, but they have the same essentially distances, a problem which will happen is that you will not be able to you need to scale the similarity score. So essentially you need to normalize this probability by some normalization factor. When I go to the math, you will see that all these probability distributions are normalized by the sum of all this distance. It's almost like a partition function we use in physics, right? So you have e to the power of minus beta e divided by all the summation over e to the power beta e. So that is something just to make sure that the fact that points are kind of sparse or close, that should not affect my ultimate map where I want to just distinguish things separately, right? So let's go again, next slide.
Hey, this is still confusing me that you're using that normal distribution to discuss these.
What would you like to do? A Gaussian?
I don't know, like, why are you talking about the distribution at all? Like, is it the distribution of the distances?
Yes, it's the distribution of the DIJs, the black arrows that I was drawing. Okay. So what it does is, so I told you the data is either high dimensional vectors or distances, right? Just pairwise distances. Mm-hmm. So now what this t-SNE does is it creates a probabilistic approach to use these distances to go forward into the algorithm rather than use absolute distances, which is what most algorithms normally tend to do. That's the difference. Okay, let's go. Okay, so this is again something where they are explaining, essentially this guy Joshua Starmer, he explains that what happens if you essentially have exactly the half, essentially. So if imagine there are these 2 points which are at a distance 0.24 and 0.05, and in the sparser cluster they are exactly at half. So if you actually divide it by all the other, you scale it, then you end up getting the same score, which helps. So the scaling, that the fact that we are having a normalization, it helps to kind of remove this factor that things are equally distant but dense or equally distant but sparse. So in this way of calculating, there's a scaled score instead of exactly the score. But okay, let's go ahead and see. Question.
When scale, you scale per cluster or scale?
Oh, per point. So for every point, you are calculating this distribution function.
Okay.
So Pij is a distribution function for point I with all other points j, except that I is 0. So okay.
One more question.
Yes.
Is this where the non-linearity is coming in?
Exactly.
In a way?
Yes.
Okay.
Because absolutely.
Do you mind repeating the question?
Is this where the non-linearity is coming in, because you're using so the theoretical premise starts with the stochastic neighborhood embedding, which is the first paper, like 2000, mid 2000. So xi is data and yi is map. I kind of told that. Step 1 is to choose a metric, and step 1 they chose an Euclidean metric, which comes with a heavy assumption. So it's very naive, it's kind of very subtle, like if you choose an Euclidean metric, it means you kind of are choosing a local linearity assumption, that points in this manifold are somehow locally linear. That becomes very difficult to relax assumption when you go to super high dimensional data. For example, there was this paper where, for example, the work I do with genomics, my cell types live in 1000 dimension space because almost 1000 genes are needed to understand one cell type, and every cell actually has 500,000 genes. Of that, only 20,000 we are actually recording, so we don't even know if that 1000 is enough. And the example which Jeff Hinton gives in the paper is actually about images. That images apparently are shown to live in 100 dimensional spaces. So that means it's something we'll go in discussion, that if you have very high dimension intrinsic, so there is two concepts. There's high dimension and there's intrinsic high dimension. So that means if the object may live in a very high dimensional space, but if by virtue of some mathematical jugglery you can show that actually I can visualize it very nicely in 2 dimension, it is a 2-dimensional object. Same goes true with images, that they are actually high dimensional, and then nobody can help you. If you are there are some kind of discussions in the paper, or we'll go there. So now let's see what this guy is doing. So we kind of touched on this idea that Dij is essentially this metric, this is the distance, Euclidean distance metric xi minus xj squared, and then it's kind of divided by a quantity, essentially the variance sigma I square is used, which is chosen in a certain way. So I will come to that, how that is chosen. But the step 1 is essentially calculate this probability distribution function Pij, which is essentially simply this scaled score. So Amir, does that answer the question? So it's just an exponential of that Dij squared, and then you sum all the others for all the other points.
Is this Dij squared?
Yeah.
Is it? It's
I guess you're asking if the
Probably
definition
not.
of Dij is that Dij squared equals to norm squared?
Oh yeah, sorry, I'm wrong. Yeah, that's Dij squared. That's true.
And you said what is sigma there?
So sigma, yeah. So what it happens is that what you do is, I told you in this visualization, you take these objects which are there in 3D and you throw them onto a 1D line randomly, right? So what does that mean? In an algorithm, it means you are kind of pulling some coordinates from a random distribution, right? So for that random distribution, you need to know what is its value, what is its spread. So that spread is an interesting concept. So that spread is sigma I square. In this paper, they kind of put it under the carpet. Around like really long time later, people started to physically understand what that means. So when this paper was published, it was said that this quantity, this sigma I square is kind of fixed or kind of chosen from the data set. So I think at that point they were just playing with it. Eventually, I think in the later paper they had a formula saying that it's 2 to the power of minus summation of Pij log Pji. So it's some kind of entropy of that distribution. So what they do is this. So this is a hyperparameter of this algorithm. So that means I didn't want to go into it because it makes the whole t-SNE algorithm look very shady. But there, so to think about it, there was this very simple thing. You want to take all these objects and throw it into a low-dimensional space by pulling it from random distributions with certain spread. That spread value initially was experimental. You can live with that. But what actually it does is this. So the physical intuition is that you want to define a hyperparameter called perplexity that essentially controls what Vijay was mentioning, how many nearest neighbors of that point you will kind of take into account when you are essentially trying to make this projection down the map, in the map. So essentially they figured out later by doing the math that if you use this perplexity value to be, let's say 10, then essentially only 30 nearest neighbors are actually used to make those attraction repulsion calculations. So you want to calculate the pairwise attraction and repulsion values between the points. So if P is 10, then 3P times 30 of those neighbors will be used, not all the points. It just makes the algorithm faster, things like that. So it's a bit of a technical point, but essentially this is how the random distribution they pick out initially. This initialization is basically done using that. Now step 2. Step 2 is essentially again creating a similar kind of a probability distribution, but instead now you are you have now projected this data in a lower dimensional space. So you recalculate your dij's, which is in this case yi minus yj squared. And in this case, again, you have a choice of what sigma you will put for this Gaussian neighborhood, right? So this sigma, they have chosen it to be half. So if you read the paper, there's a little typo there. They say 1 by square root is the variance, but variance is actually half. Well, I think what they meant, the standard deviation is 1 by square root. But that's fine. So this is essentially, now you have cooked up two distribution functions, one in a high dimension, another in low dimension. Now step 3 is to create a cost function, which is basically trying to make these two distributions as much as possible, similar, but kind of trying to. So how do you do that? So how do you compare distribution function? So that is basically a standard technique which is using the scale divergence. So what you do is yes. Okay.
So I didn't get where they get Qij from. Is that
Okay.
like they assume that and like
No. So what you did is you took these points,
Yeah.
right, and you threw it in a lower dimensional space, right? So in the low dimensional space, you have this randomly distributed these points. So now you can again calculate in the low dimensional points all the pairwise distances.
Mhm.
And so from that pairwise distances, you calculate this, essentially, this quantity.
So essentially they initialize the map with a random
Exactly.
mapping and
Exactly.
then try to.
It's an iterative process, exactly. And so now once you have Pij and Qij, you essentially are comparing Pij and Qij using the Kullrich-Leibler divergence technique. So to make it like just for me to understand it, I actually try to understand it from here. So essentially, for every point there is a KL term. So a KL term, KL Pi Qi means the comparison of, for just the ith point, the P and Q distributions, right? Now you have a summation of all these over all the points. That's the total cost function. Okay. And step 4 is you want to minimize this cost function. So there is something interesting here at the KL divergence, that this KL divergence has certain properties. So one of the properties is that it's asymmetric, right? And so we will come to that, what that means. I have an interesting point in the next slide about the KL divergence, but let's look here. So what this step 4 does is, it's a little tricky calculus. You could do that if you want at your home. So you basically take a derivative of C with respect to yi and you end up getting this term. So if you look at this term, what happens, obviously what happens here is, do you guys understand this kind of a little nuance that Pij is not same as Pji? This is an interesting nuance because what it just means is that if you think about 3 points, you can try to cook up this in your mind, that if you have one of the points fixed and you have 2 points here, the distances are these, but Ji may be different. These are these distances, so they are not the same. So essentially in this original SNE version, it was called an asymmetric version where Pij and Pji were allowed to be different. Later they had a second variant, which was, they said we'll just sum them up and divide by 2. So they averaged the 2 and they call it the symmetric SNE. The result of that was that nothing changed. The algorithm was still slow and it produced equally good visualization, and in certain cases maybe slightly better. So they said that since the computation just is a little easier, because this gradient function looks more cuter, because then you end up getting 4 here, and then you have essentially Pij minus Qji. And then it looks very similar, already it looks very similar to this equation that we are familiar in classical mechanics. By that negative gradient of potential energy is spring constants time displacement, right? F equal to kx. So it looks a bit like that. So this is basically the potential, the cost function that you are minimizing. There is a spring constant here, and this is basically the distance, and it's attractive or repulsive depending on how your yi, yj, and these values, depending on how these values, Pij and Qij's, are matching up to each other. Yes, yeah.
Is it true that if you set perplexity to be large enough, then Pij equals to Pji? Pij equals to Pji.
If perplexity is very large enough, no, it does not. Because think about it, perplexity is what it is doing is, it essentially asking you to look at how many points in the neighborhood you are. So if you say that if Pij is super large, essentially it's looking through all the points, but it will just mean that essentially these QIJs are highly ineffective. So when you calculate QIJs, they will not be good enough that your final map will be just not a good cluster. So one of the things when you practically implement t-SNE is you want to see very granular clusters which are super dense, super far away from each other. And if that is happening at a certain perplexity, you stay there. And I will come again to this concept that why these things are a little bit shady. Like why is Perplexity changing the whole optimization game? Because this cost function, this KL divergence, is a non-convex cost. So as a result, what does that mean? Convex functions have a global minima. So you can minimize it a lot, and if you minimize the hell out of it, you will get a same solution all the time. But because this KL divergence is not convex, is non-convex, it essentially creates problem that every time you get a different solution. This was solved by the fact that they figured out a nice sweet spot of all these hyperparameters. This is the first hyperparameter which I introduced. There will be 3 or 4 more. But they figured out basically a sweet spot of all these 4 hyperparameters. That works for all big data sets, from Netflix data to all the way to genomics data. So that's kind of why this thing stuck around the way it was. So yes. Okay. Yeah, so this is basically taking now doing gradient minimization. So this is the update rule, which we saw del C del Y. So this is basically how you will update at every point. You have going through this iteration constructively, right? So you have thrown them on the lower dimensional manifold, created this beast QIJ, compared it with PIJ. Then you essentially go back again. So this is basically, so here now the other hyperparameters start to get implemented. So there is this parameter called learning rate, which I'm sure you guys are more aware of. And then there's this momentum, which essentially is a forced hyperparameter which was introduced because it was shown that it makes the algorithm faster. So this was this alpha term which was there. They also did something interesting there, that they added some kind of Gaussian noise, which is like simulated annealing, and apparently as they went down the convergence, they would take out the Gaussian noise slowly out. So that's the kind of almost like how you tweak up the temperature of the system and slowly bring it to 0, right? So mutation 1 to this algorithm happened within the classic paper of the t-SNE paper. So then they first published, the second paper was published. They already said that symmetric SNE will be the first change to our algorithm, and then there will be a second change. So the first change was simply this, that they basically made Pij equal to Pji and Qij equal to Qji. And this has some implication, which means that if now this is the way you kind of make the new definition of Pij, which is the sum of the 2 conditional probabilities divided by 2 times n, where n are all the nearest neighbors. But this apparently does something interesting in the algorithm, which is an intuition which I am still not completely developed. But this is what is argued in the paper. So apparently, if you don't do this, what happens is if you have an outlier, if you have a point which is super far away, that point so very far has very low Pij, right? So because it has very low Pij, apparently in the cost function, it plays a very little role. So they figured out that that was an issue, that once you do this version of symmetric SNE this way, all the points apparently have equal weightage now from the map. That's something that they argue in the paper, but I did not completely understand that. So if anybody wants to tackle that.
Like it's like if you look at that in that paper, they have talked about the gradients and all. So if you look at the gradient associated with the SNE as such, it's almost 0 everywhere. But what they wanted to do, I think, this is my version probably. What they wanted was for some repulsion to exist, so that the iterations can, like if for example 2 points are from the beginning, like they are set far apart, it should not happen that they remain like that. There has to be, they have to be included. So what they want to do is that include some sort of a uniform repulsive force between the points, so that there is some sort of computation taking place, and we see them included in the clusters. So expect that if the points are separated in the high dimensional space, we still want them to be included in the clusters, right? So what we visualize. So this was just to bring in some sort of repulsion to, so that, there is this, they could counter the problem of, excluding these points.
No, I think what you're saying is different. That is the answer to why you use T distribution. So the thing was, so I think I may be wrong, but what happens is that both in SNE and symmetric SNE there are attractive and repulsive forces. The problem with SNE, what happened was that all the far points started to come to the center of the map. That's what they say, right? So what they said is that why does that happen is that yes, we do have attractive and repulsive forces, but if there are large number of points which are far from, let's say, a cluster, those small for each of those large clusters, those small effects sign add up, and they all start to come to the center. So they said that we need to make this repulsion much larger, so that if there are far points, they stay far, but if there are close points, we can embed them in a cluster. So it's sort of something to do. So when I explain this t-SNE part, I will explain this, so don't want to give away the fun of it. So let's go to the next slide, I will come to that part. But this is something interesting. You have to look in the paper that they say why somehow outlier control is done with the symmetric SNE. I am not sure.
Sorry, I'm lost. How does this help boost the repulsion? This formula?
This formula, that's the thing which I think I'm kind of holding off right now,
okay.
because I know that there is a statement like that on the paper, but I should have read probably more carefully. What they do say is that by doing this, the weights of each points becomes same. I don't know.
I don't want to take the time, but it's related to the gradients, because it was observed that the gradients become zero. Like if you look at the del C by del yi, that used to become zero. So they wanted to prevent that, and from that they wanted the summation to not go below 1 by 2n.
Okay, I see.
So that
we have a plot of that. We will see. Maybe we'll come back and figure that out from the gradient picture. Okay. Yes.
That's a good point, but I didn't quite understand. So the fact that summation goes below that means that the gradient might go to zero?
Yes, so the gradient, there would be no change. Like it would, like most of the points, like he will show. So you have the plot where they talk about the heat map, and they are plotting the high dimension.
They are plotting. If you go to the next previous slide, so they are basically plotting this function for SNE and t-SNE, and you can see that there is some differences between the two, but it's hard to pin that down, because in the gradient picture you already have these two changes, not one only. So it becomes SNE. So t-SNE has two major changes, right? It becomes symmetric SNE, and it stops using instead of Gaussian neighborhoods, it starts using essentially t-distributed functions. And because the reason for that is essentially, you'll go there. We have something like that. So let's go further.
There's one more paper,
yes.
like towards data science. There's one person who has talked about the exact thing.
Okay.
So I was reading about that.
I should have added that. Yeah.
So when I read that, I was able to understand that it's related to the gradient. That's why they don't want it to fall below 1 by 2.
Okay.
I guess one thing about Pij is that that's summation over j, so what you're getting is like marginal probability for I, and that marginal probability has a lower bound and it's never going to be 0.
Yes.
Is that what you're trying to achieve here?
Okay. This is a little bit of a digression. We have kind of touched on most of this. So Pij is asymmetric. This I think all of you guys probably understand that, right? That if you just think about this with 3 points, you will be able to cook it up. It's how Pij is defined. So the other thing which I want to kind of get you guys on board is with this understanding that how exactly t-SNE manages to make locally, in the map, locally embedded points which are close, actually are close in the high dimensional point, but if points are very far apart in the high dimensional point, in the data, they may be actually close in the t-SNE, but they don't really, so there is far points in the high dimensional data are given less value when you are trying to fold it. So how does that all kind of come into the in this picture is like this. So closer points, let's say, have a cost called CA, which is closer points is Pij is high, and far points we know is Pij is low, so they have CB. So the cost function, which is basically for single point, now I'm just writing for one KL divergence. So this is basically this function Pij log Pij by Qij. So I can just make it log A minus log B. So I get these two terms. So this term is essentially constant, and this is the term which essentially is the other term, which is Pij log Qij. So now, naively, what is mentioned in the paper is that the cost A is greater than cost B. That means the cost for points which are closer, if you keep them far apart, you have a higher cost in the way the KL divergence is cooked up. But if points are far apart, it's also high, but it's less than the other cost. So because CA is greater than CB, widely separated points can be collapsed as nearby points in the map, which is sort of a drawback of t-SNE, but it does ensure that close points in the data become close points in the map. That's basically somewhat there in this asymmetric construction of the KL divergence. I know that it's not super clear, right? So yeah, but I think what is important is just this part. If you stay with that intuition, I think that's good. That there is a cost which is for far points, and there's a cost which is for low points. But cost for far points is lower than cost for lower points, for closer points, and that essentially ensures that closer points in data space become close points in map. That's essentially there. But it's somehow there in the KL space, like, if you start to compare, the reason that this intuition I cannot build super strong is that we need to know a few things more, like whether Pij divided by Qij is always close to 1, and then from there you might be able to say, because Pij is high, so this cost CA is high than if CB cost is low. If that is.
May I add something, because
yes.
There is one YouTube video by Ali Godse of University of Waterloo. So there he explains it in a very simple way, like when usually when Xij, I'll be very fast. So when Xij are very close, your Pij is very large, and if you see why it's asymmetric is because you are not only having it in the log function, but it has an influence on the overall, the product, because you have Pij multiplied by log of Pij divided by Qij. So that's the main part to focus on, because when Xij, when we talk about the high dimensional space, and Xi and Xj are closer, Pij becomes large, and if we represent it using points in the Q space with far apart points, the Qij would be very small. So the overall cost would be more, as he was saying, for a point that is for closely represented, like for a close points to be represented with faraway points, as compared to faraway points being represented by close points.
Yeah.
So it doesn't impose that much penalty to faraway points. It doesn't even care about those faraway points, because that would essentially increase only your Qij, but the cost would not increase. If you see, the cost would only increase if your Pij is large and Qij is less, and that is the cost associated with representing nearby points with far away.
I think that's a beautiful and succinct way to put in forward. I always try to get like easy access, so I say, you know what, I mean, IRE style, log Pij Qj is order 1, because that's what we want to do. We want to match the distribution. So close points, Pij is high, so cost is high, fast points is low. So I directly tried to do it with this leading order term and took out the log term, but I think you had a good intuition. Like, think about, what does close points in Qij mean? It also means that Pij is high. It also means Qij is high. So, which is an intuition I developed for you guys, right? Close points, higher probability. Second intuition that I want to develop is, again, a bit tricky intuition, but let's do this. So, first thing is, there's two different things. I want to kind of explain how curse of dimensionality starts affecting and why this is a very difficult problem. So, first thing is, imagine you have points living on a circle, right? So 2 points are on a circle, but they're super close to each other. So that's like local linearity. You can kind of use an Euclidean metric, and you can unroll this thing, and everything looks nice, right? So you can do this kind of a dimension reduction technique without loss of any properties. So that works. So, but generally, this is what Greg Hinton develops this intuition in the paper, that generally this is not possible. So, for example, imagine you are an ant in a one-dimensional space. So, how many ants can be in a one-dimensional space which are equidistant to each other? Only 2. So, this is basically, these are 2 points which are equal distance to each other. So, in 1D space, you can have this. So, if you are in 2D space, you can have 3 points which are equidistant, mutually equidistant from each other. So if you are in a square, you will not be, because then 2 points are on a diagonal, right? Now, if you are in a 10-dimensional object, you can have only 11 equidistant points. Now, he drops the bomb. He says, now if you actually have that kind of a data, and you want to unfold it into a 2D space, because that's what you want to do in t-SNE, how do you manage to do this? So it's a problem which intrinsically is not easy to solve, and that's a very nice intuition I think he developed. The second intuition, which I think people who do string theory have already this very strong understanding, which is that the more higher you go in dimensions, data starts to, so imagine if you have uniformly distributed data in 3D, it's on inside a cube, let's say all the data, you can draw a circle, most of the data will start to stay inside the circle. But when you go to higher and higher dimension, what happens is this data starts to stay closer to the corners of the cube. So you have essentially a n-dimensional cube and an n-dimensional sphere inside it, but that n-dimensional sphere is almost empty. So most of that data points are at the corners of that cube, n-dimensional. So this is called a spiky sphere problem, that in high dimension data tends to stay in actually in very localized objects. So that actually is the counter.
Not that the data is staying.
Not
it's
that
the sphere, the volume of a sphere in n dimension
is
compared to the n cube is actually much smaller.
Much smaller.
There's a lot more volume that is in the
corners of the cube,
of compared to like 2D or 3D. If you build your intuition that way,
yes,
is that n-dimensional sphere actually occupies a much smaller volume of the cube.
Yes, yes,
that's
exactly.
Yeah.
So that's where I think the second intuition is that because essentially all the data gets concentrated in the corners, there is hope that a low dimension.
It doesn't. I think that's what I'm trying to say. I don't think the data gets concentrated in the corners.
Mm-hmm.
It's that the sphere doesn't actually occupy enough space.
Yes.
So even if the data is uniformly distributed, a lot of it is actually outside
the sphere, right?
Yeah.
So what they say is because of that, that essentially means that several of those dimensions are not useful. So you could actually project it back to a low dimensional space. That's what kind of is the argument. That the reason that many of this, I think the argument is this, that many high dimensional objects, many high dimensional things are actually not living in an intrinsically high dimensional space. They live in a lower dimensional space. And if that happens, you can project it back. So I think it's like two different arguments, but maybe wrong. I may be wrong about this whole thing.
But it sounds like it might be a property of, like, maybe the data lives on a manifold inside.
Yeah.
The data has to live, yeah, you're right. So if the data actually lives in a lower manifold, then only you can visualize it, right? So and most often real data sets have some kind of a lower dimensional visualization, representation. Okay, so let's go forward. So this is basically t-SNE. So we have already touched on a couple of points. So first point was that you kind of symmetrize these probability, the conditional probability Pijs, and then the second point is essentially that in the step 2 that Pij is chosen exactly the way it was done in SNE, the same normal distribution, that same weird sigma I with its perplexity, everything remains the same. Then Qijs, instead of now having a if you remember, there was a Gaussian neighborhood with a 1/2 variance that I was using. Instead of that, they are just using this Cauchy distribution now. And the reason for that is, if we can quickly go to the next slide and then come back. Oops, sorry, we didn't put it. Okay, so okay, no worries. What happens is that if you draw a Gaussian distribution with a t distribution, so it's kind of a little shorter at the peak and little fatter at the tails, the t distribution. So, right?
Yes.
Yeah. So as a result, because of that, what happens is essentially that this allows overcrowding. So essentially, SNE, there was this problem that all these far points, which essentially have low Pij values, they start to get less represented with the t distribution because they have like fatter tails and things like that. And then that's basically the major change. The KL function remains exactly the same way you would calculate that log Pij log Qij term. The step 4, which is the gradient of the which is the gradient function, that one essentially has an extra term here. So still has the spring feature, but you have an extra term here, which is 1 by distance squared. So now we'll go to the next slide. Yeah, next slide. I will end this first half of the discussion with basically churning everything in the next 2 slides. So essentially, this is what was the algorithm. You all kind of have gone through it, like with me through the math, but essentially in one slide, you start with data, high dimensional vectors. You have a cost function. You have chosen a hyperparameter perplexity. You have number of iterations, how many times you will run through the loop. Learning rate, momentum, everything we kind of saw. Then the result is the low dimensional map, yi basically. Then you compute Pijs, compute again the gradient of the cost function, have new basically values of the y, and then go back again. And you keep doing it. So what happens is, so again a small intuition, because if you remember the cost function del c del y, it had a yi minus yj term, right? So what it does, it means that because as you're minimizing this cost function, these points in the low dimensional manifold start to move. And that's kind of what we saw in that visualization, that because of this attractive and repulsive forces, they will move, and they will move until and unless you kind of converge to some kind of a visualization where you feel that I don't want to move anymore, which is controlled by the number of iterations. Okay, let's go forward. Yeah, so this is actually a new paper which just came out this year. This kind of, if you don't want to read 4 papers, I think this is the best paper to read. You can have like the whole overview here. It's kind of the whole, the visualization is not great, but it kind of goes through the whole thing which we discussed. And the only cute thing which I will kind of try to point out here is that. Did I touch everything? Yeah, I think it's fine. Yeah, I think it's fine. Don't worry about it. So yeah, so now we'll probably stop and have some discussions.
All right.
Okay.